Hello students and welcome to my channel. Today I have come with questions based on optics which were asked on 30th January 2023 JEE Mains. So without wasting time, let us start solving this. Here comes the first question. A person has been using spectacles of power this much, -1 diopter for distant vision, and a separate reading glass of power 2 diopters. What is the least distance of distant vision for this person? Now, students, certainly this -1 diopter is used for large distance, long distance, because a concave lens rectifies what is known as short sightedness. That is, we cannot see a objects at a far off distance. So it has nothing to do with near point. Now coming to this 2 diopter, this is a convex lens because power is positive, and a convex lens is used to rectify the far-sightedness. That is, the person is not able to see near objects. Okay. Unlike a normal person whose this distance of distinction is 25 cm, here it must be beyond 25 cm. That is the reason why he is forced to use a convex lens. So the idea is, if the object is actually located at 25 cm, okay, the person should be able to see the object because the image should form at the near point. Whatever be is near point, image should be formed at the near point, and since he can see things beyond his near point, so certainly if the image is formed at near point, he can see. So based on that, so this is redundant. Okay, it's not required actually. We don't require this anymore here. Now, for this, you see, there's a convex lens of focal length. We can find the focal length as 100 upon power in diameter. You will get in centimeters. Okay, so this is 50 centimeters. So now the object should be placed at least distance of distinct vision, that is 25 cm. Now light rays starting from the actual object after passing through the convex lens should converge and appear to come from the near point. That is the idea. This must be the near point. So that before entering the observer's eyes, it should appear to come from N, and obviously he'll be able to see. So this is the eyeball, okay, and this is the retina. This is the eye lens, and image will be formed exactly at the retina. So this is the idea. So this distance should be his least distance of distinct vision. Okay, least distance of distinct vision. So this for now I write it as D, which we have to find out. Okay, and focal length is, being a convex lens, focal length will be plus 50 cm. Okay, right. So using the Gaussian form of lens equation, we have 1 by f is equal to 1 by v minus 1 by u. Okay, that is 1 by 50 cm. I am substituting all the quantities in centimeters, so don't worry about the unit. Now, since object is to the left of the lens, so I'll write minus d here, and sorry, image is to the left and object is also to the left, so I should write minus 25. So therefore 1 by d, if I bring 1 by d this side, then I'll have 1 by 25 minus 1 by 50. Okay, so this will be 1 by 50. Therefore d is equal to 50 centimeters. So the correct answer is the C option, 50 cm. I hope that is clear, students. Moving on to the next question. A thin prism P1 with an angle 6 degree made up of glass of refractive index 1.54 is combined with another prism P2 made from glass of refractive index this much to produce dispersion without deviation. So you can see without average deviation, means there is no deviation here. So we have to find the prism angle P2. In other words, we have to apply the condition for no deviation. Now, what is the condition for no deviation? Condition for no deviation, no net deviation is that net deviation must be 0. In other words, deviation due to the first prism plus deviation due to the second prism must be equal to 0. Now, as you know, the mean deviation is given by mu minus 1 into A, and here also mu dash minus 1 into minus A dash, because the other prism should be placed in an inverted manner. You know, in order to have no net deviation, the two prisms should be placed in an opposite manner. In other words, the base of the first prism and the base of the second prism should be opposite. The base of the first prism is at the bottom, base of the second prism should be at the top. So that's why I have taken minus A dash. Now let us substitute here. So mu for the first is 1.54, minus 1 is 0.54. So I'll write it as 54 by 100 into A. A is 6 degrees. Then mu dash minus 1. Mu dash is the refractive index of second medium, second prism, 1.72, minus 1 will be 0.72, 0.72 I'll write it as 100 into A dash. So we can remove 100 from here, and also we can cancel by what? We can cancel throughout by, I guess, 18, I guess. Yes, we can cancel throughout by 18. So 18 4s are 72, 18 3s are 54. Now 2 2s are 4, 2 3s are. So we have 3 3s are 9 by 2, that is 4.5 degrees. So B option is the correct answer. Moving on to the next question. In an experiment for estimating the value of focal length of converging mirror, image of an object placed at 40 cm from the pole of the mirror is formed at a distance 120 cm from the pole of the mirror. These distances are measured with a modified scale in which there are 20 small divisions in 1 centimeter. So the value of error in measurement of focal length of the mirror is right. So now you know the object distance 40 cm from the pole and image is formed at a distance 120 cm. So image distance is also known. So we have to find the error in focal length. Now using mirror formula we have this. This is the mirror formula. Okay. Now for a converging mirror, that is concave mirror, as you know, objects is to the left of the mirror, image is also real image, so image is also to the left of the mirror, and focus is also to the left of the mirror. So all these will be negative, so minus will get cancelled. So no need to write minus minus minus. Okay. Okay. Now whenever you have to calculate the error in these kind of complicated formulas, particularly you have fractions here, as you can see, 1 by f is equal to 1 by v plus 1 by u and on. So, or simply you can differentiate, sorry, no need to take log here. So for 1 by f it is minus 1 by f square into error in f. Here 1 by v it is minus 1 by v square into error in v plus 1 by u it is minus 1 by u square into error in u. Okay. So from here I can write error in f is equal to f square divided by f square is equal to error in v upon v square plus error in u upon u square. Now we require v, isn't it? So we have to apply the mirror formula because object distance is 40 cm, image distance is 120 cm. So we can find what v. So 1 by f we have to find. So 1 by f is equal to 1 by v plus 1 by u. So v is minus 120 and u is minus 40. So we require f. So f will also automatically be negative value. So this will be minus 1 by 40. If I take common, I have 1 by 3 plus 1, which is 4 by 3. So here as you can see 4 gets cancelled. So F is minus 30. So numerically it is 30 cm. Okay, right. Now since the object distance and image distances are measured with the same scale, so error will be dependent on the instrument rather than the quantity which is being measured. Okay, because we are basically focusing on instrumental errors, and instrumental errors we take it as the least count, which is also known as least count error. So what is the least count of this? You can see 1 upon 20 cm. That is the least count. So that will be taken as the least count error. So here we have, so substituting this, we have delta F by 30 into 30 is equal to 1 by 120 into 120 plus 1 by 40 into 40 into delta U. Delta U is 1 by 20. So we have to cancel zeros throughout. Zeros have already been cancelled. Now, sorry, we are left with delta F by 9 is equal to, we can take 4 into 4, 16 common. We will be left with 1 by 3 and 1 by 3 plus 1 into 1 by 20. So which implies delta F by 9 is equal to 1 by 16 into 10 by 9 to 1 by 20. So therefore 9 and 9 gets cancelled, 1 0 gets cancelled, we are left with 1 by 32. So K is 32. This is the answer. Right? Moving on to the next question. Sorry. In Young's double slit experiment, two slits S1 and S2 are d distance apart, and the separation from slits to screen is d, as shown in figure. Now, if two transparent slabs of equal thicknesses, this and this, are introduced, but refractive index indices this are introduced in the paths of beams, then S1 and S2, then central right fringe spot will shift by. Now, students, we have to understand, if you understand the basic concept of Young's double slit experiment, then you will realize that at the central right fringe, okay, I'll just elaborate the details here. So this is the screen, let us say, these are the slits here. This is the central line. Okay. Now at the central line, the path difference between the interfering waves is 0. Path difference is 0. In the first, at the position of first right fringe, the path difference is 1 lambda. Path difference is 1 lambda. Similarly, at the position of the second right fringe, the path difference between the interfering waves is 2 lambda, and so on. That is corresponding to every path difference of every 1 lambda, there exists one fringe. Okay. So over an interval which corresponds to a path difference of 1 lambda, there exists one fringe. That is the basic principle. So if we can evaluate the path difference changed because as a result of the introduction of the slabs, if we can evaluate the change in path difference as a consequence of introducing these transparent slabs, then we can get an idea of the number of fringes that crossed the central right fringe in terms of this. So our first step will be to calculate the change in path difference as a result of the introduction of the two slabs. Now, for the first slab, or in general for any slab, the change in path difference is this, where mu is the refractive index of the medium, T is the thickness. which can be written as mu minus 1 into t. So this is the change in path difference, or change in optical path, we can say. Change in optical path. I should write change in optical path. And the difference in optical path is nothing but the path difference. For the two different waves, the difference in their respective optical paths will give you the change in path difference. So, change in path difference is nothing but the difference in the changes in optical paths. Difference in changes incurred in optical paths of the two waves, for the two waves. For the first one it is mu1 minus 1 into t. For the second it is mu2 minus 1 into t. So we have to obtain the difference, students. Whichever is larger, from the larger we have to deduct the smaller. So finally you have the difference between the refractive indices multiplied by thickness. Okay. So what is the difference in refractive indices? You can see 0.04 into zero point 0.1. So this result will be 0.04 multiplied by 0.1 mm. 0.1 means 1 by 10 mm. Okay. So I can write this as 4 into 10 power minus 6 meter. Okay. Or I can also write this as, if I multiply and divide by 10 power 4, I can write it in terms of angstrom also. Now, as we discussed just now, a difference in path difference corresponding to 1 lambda results in 1 fringe. So that means if you divide this result by lambda, and lambda is 4000, you get the number of fringes that cross the center bright fringe. Is it? So the required number is the total change in path difference, which is 40,000 degree angstrom, divided by lambda, and lambda is 4000 degree angstrom. So in all we get 10. So 10 fringes would have crossed the central right fringe. So I hope that is clear. Let us move to the next question, please. In a Young's double slit experiment, the intensities at 2 points for the path difference lambda by 4 and lambda by 3 are I1 and I2 respectively. If I0 denotes the intensity produced by each one of the individual slits, then I1 plus I2 divided by I0 is. So this is simply formula based question, students. Suppose you have a Young's double slit experiment here. The setup, these are the slits here. Okay. This is the screen here. Now if the intensity is due to each slit or each source is I0, then the resultant intensity at any point is 4 times of I0 into cos square of phase difference by 2. Then what is phi? Phi is the phase difference between these two interfering waves. Phase difference between these two interfering waves. So this is the formula. I hope you are aware of this. Also we know that a path difference of lambda is equivalent to a phase difference of 2 pi radian. This is also known to us, isn't it? So accordingly, a path difference of lambda by 4 will be equivalent to a phase difference of 2 pi by 4, that is pi by 2, that is 90 degrees. And a path difference of lambda by 3 would correspond to a phase difference of 2 pi by 3, that is 120 degree. Okay. You can write them in degrees because as you write in degrees it is more convenient. So accordingly, we can get I1 and I2 by substituting these values in the place of phi. Here, phi is the phase difference between the interfering waves. Right. So coming to the first case, I1 will be 4 times I naught, or we'll do one thing. We'll just substitute this. We'll substitute this here. The required expression is I1 plus I2 whole divided by I naught. In other words, we have I1 by I naught plus I2 by I naught. So I1 by I naught is 4 times of cos square phi 1 by 2, whereas I2 by I naught from here is 4 times of cos square phi 2 by 2. So here 4 cos square phi 1 is 90, so 90 by 2, that is 45 degree, and here cos phi 2 is 120 by half, 2 divided by 2 is cos 60. So this will be half and this will be 1 by 4, that is 4 into 3 by 4, which is 3. So correct option is 3. Then moving on to the next question. All questions are done. So that's all students in this video. Thank you so much. Okay.